Okay, so in this video we will work on a kinematics problem related to a rolling cone, and let me explain the problem. So assume that there is a cone that is lying on a horizontal surface, and so this is the cone, and let me just right, so the cone is lying on a horizontal surface, and the angle that is made by the cone with its axis is beta. So this angle is beta. The base of the cone is of course circular with a radius r, and let's say that the center of the circular base is O prime. The vertex of the cone is at O, and at a given instant the this point of contact of this base circle with the ground is C. And furthermore, in this problem we will say that the cone is turning with an angular velocity omega on this horizontal surface. So first of all, cone rolls without slipping, okay, and now and it is rolling with an angular velocity of omega, which essentially means that the point O prime goes in a horizontal circle let's say this vertical axis is Z through this vertex O. So the point O prime goes in a horizontal circle, about Z at an angular speed of omega. Okay. Now let us say that there is a point P on the circumference of this base circle, and let's say that it is at a certain arbitrary orientation at a certain point, at a certain instant. Furthermore, let's say that the point P at that instant makes an angle, or rather the segment O prime P makes an angle phi with this diametrical line, which is going through C, through O prime, and through the topmost point of the base circle. So in other words, if you took a view from A prime So the view AA prime would look like this. So that's the base circle of the cone, and C is here, O prime is here, and here is the line joining C and O prime going through the topmost point of the circle, and the point P is somewhere here, and O prime P is making an angle phi with respect to this line through C and O prime. Okay. Now if you took a side view of this is kind of a perspective view, but if you took a side view of this cone, what you would see is just an isosceles triangle. So essentially the side view of the cone is going to look like an isosceles triangle. This would be your point O prime. You won't be able to see the point P if you took a side view. This angle is better, this angle is better as well. When you look at this from the side view, this distance would be R. I haven't given the problem statement yet. I'm still defining the cone because it's important to understand the geometry of the problem before we start solving it, or start solving whatever the problem is. All right. Now, for the sake of completeness, I'm going to in this diagram, I'm going to say that as this turns, as the cone rolls on this horizontal surface, you can see that the base circle of the cone is turning in this manner. So the base circle is actually turning this way, right, with an angular velocity of phi dot, which basically means that the cone, because of its roll without slipping, as it turns about this vertical axis with an angular velocity of omega, the cone itself spins about its axis. Okay, and that spinning angular velocity is given by phi dot, right? So that's the you could say it is the side view of the cone. Now the question that we ask is the following: assuming roll without slipping of the cone, what is phi dot given omega? So that's the question. What is this spinning speed of the cone given that it rolls on the horizontal surface, and as it rolls, the angular velocity that is traversed by O prime is given by omega. another way of looking at this problem, and still we are doing a kind of a geometric, trying to get a geometric understanding of this problem. If you looked at this cone from the top, so let's say I took a top view, let's call that view B prime. So view B prime. Now that view is going to look somewhat like this. I would see the cone forming an isosceles triangle. This point O prime is shown. Now when you look at the cone from the top view, notice that C, the point C, is going to be just underneath O prime. Okay, that is one consideration. The point O is here. The z-axis is actually going to be pointing upwards, perpendicular to the surface of the page, and the cone would be turning with an angular velocity omega. It would have a spin about its axis, and that spin is phi dot. And the interesting thing is that this point O prime, if we look at the cone and its motion from the top, it's going to be simply tracing out a circular path. Okay, and that path would have a radius given by this distance capital R, which we have to find out, but this distance capital R would be the circular path taken by O prime about the point O. So O prime makes a circular path about O with an angular velocity omega, right? And again, even if you're looking from the top, the angle that you would see formed by the isosceles triangle is 2 beta, so beta on either side of this median or perpendicular. So this is the geometry of the motion, and our goal, let us go back to the goal of this problem. We want to find out what this phi dot is. Clearly, if the cone is rolling without slipping, you can imagine that phi dot is going to be directly dependent on omega, because they are not independent due to the rolling. Okay, so because of the rolling, this spin angular speed is determined by this rolling angular velocity. Now, to solve this problem and to find out how phi dot is related to omega, we are going to choose a rotating coordinate frame. That rotating coordinate frame is going to look like following. So we have already shown the z-axis. As you can see, z is here, z is shown here, and we showed z here in the perspective view as well. Now our x and y axis are going to be like this. X is going to be horizontal, and it is going to be in the same direction as the horizontal component of OO prime. So keep in mind the phrase, it is in the same direction as the horizontal component of OO prime. Okay, and y is also going to be going to remain horizontal, and it is going to be perpendicular to x, and you can see that x, y, z, they form a right-handed triad, meaning if I curl my fingers from x to y, my thumb will point in the direction of z. If I curl my fingers from y to z, my thumb will point in the direction of x, and if I curl my fingers from z to x, then my thumb is going to point in the direction of y. That's a right-handed coordinate frame. So you could represent that as x, y, z like this. Typically we use I, j and k as the unit vectors along x, y and z respectively. So we are going to have I, j and k along the directions x, y and z respectively, and we are going to use these as the unit vectors. So they will follow that same rule for carrying out our cross products. Now if you take this xyz coordinate frame and if you now project that coordinate frame over here, what we will see is x is in this direction, y is into the surface of this page going perpendicularly inside, and z is pointing upwards. So now you see that x is not really in the direction of OO prime, but rather x is in the direction of the horizontal projection of OO prime. And so when you look at the cone from the top, the horizontal projection of OO prime is not visible, and therefore it seems like x is along OO prime, but really it is along the horizontal projection of OO prime, as evident from here, right? And this diagram is kind of a perspective view, so I'm not showing the x and y over here. This is kind of you can assume that this is kind of an approximate view because I'm showing the face of this base circle, which strictly in side view is not going to be visible. So this is, let me call this the side view. So these three diagrams are actually forming the engineering diagrams for this cone. And now note that our coordinate frame xyz is a moving coordinate frame according to the way it is defined, because we have defined x to be always along the line OC. So let's clarify that. So x along OC. So C is the instantaneous point of contact of this base circle with the ground, and so as the cone rolls, that point C is also going to change, but the x-axis is always going to be along the point from O towards the point C. So it's a rotating coordinate frame, and y is of course just perpendicular to x on the horizontal plane. Okay, so this is the setup, and we want to find the phi dot, the variable phi dot given omega. Okay, so how do we go about it? Our strategy is going to be the following. Our strategy is we make the observation that O prime takes a circular path, and so if this angular velocity is omega, we can find what this velocity O prime is rather simply because O prime just goes in a circular path about the point O. So that can be easily found out. Then what we will do is we will impose the fact that because C and O prime are on the same rigid body, C is the point of contact with the ground, but it's on the same rigid body. So there is a definite relationship between the velocity of C and the velocity of O prime. We know the velocity of O prime. We also know that the velocity of the point C is 0, and that is because of the rolling without slipping. Because the cone is rolling without slipping, the point of contact or the points of contact of the cone with the ground, they all have 0 velocities instantaneously. So in fact all these points which are in contact with the ground have 0 velocities. So we can use that and come up with an equation that relates the velocity of C with the velocity of O prime. And once we have that, then from there our hope is that we will get the angular velocity. We will get a relation that will relate phi dot to omega. So that's the process that we are going to follow. Now let us first come up with an expression for V O prime. So let me just indicate V O prime over here. So you can see in this diagram, since O prime is following a circle, the velocity of O prime is going to be directed this way. It's going to form a tangent, okay, and the velocity itself is going to be the angular velocity omega times this distance capital R. So in fact the velocity O prime, V O prime, let's talk about the magnitude first. So the magnitude is going to be omega times capital R. Right? Now, what is this capital R? Well, let's for a second go back to this diagram where we have shown the side view, and you can see from the side view that capital R is this distance. It is the horizontal distance, horizontal projection, or the length of the horizontal projection of the segment OO prime. Okay. Now, how much is that? Well, let us say that the height of the cone is h. Okay. If the height of the cone is h, then you can see that R is equal to h cosine beta. So we come back here and we say that this is omega times h cosine beta. If you go back to the side view here, you will see that the cone forms this right angle triangle with the ground, and if this distance, the height of the cone is h and the radius of the base circle is r, then tan beta or tangent beta is r divided by h. So going back, we have tangent of beta is equal to r divided by h, which in other words means that h sine beta is equal to r cosine beta. Okay. So this is another identity that will be useful. So here is our angular, the linear, the velocity of the point O prime, and if you express O prime as a vector, it is omega times h cosine beta. Now in terms of the vector, it is always going to be parallel to the y-axis, so it is going to be in the j direction, right? No matter in what orientation the cone is, because this is a rotating coordinate frame, so it turns with the cone, and so the velocity of O prime will always remain in the direction of y. So that's going to be the representation of the velocity of O prime at any instant, right? Furthermore, since again going back to this figure here, since C is here and O prime is here, and C and O prime are on the same rigid body, we can then say that velocity of C is equal to velocity of O prime plus of course velocity of C with respect to O prime. And because C and O prime are on the same rigid body, so we can say that the relative velocity is omega cross rho C with respect to O prime. Okay, and this is due to, since C and O prime are on the same rigid body, or they are parts of the same rigid body. Okay, C and O prime are points on that same rigid body. Okay, now now here we have to keep in mind that omega is the net angular velocity of this rigid body, and so now let us resolve the angular velocity of this rigid body. So you can see that the angular velocity of this rigid body, the cone, comprises of two angular velocities. One is this omega, and the other is the fact that as the omega causes the roll ensures that there is a certain phi dot, and phi dot is then the spinning angular velocity of the cone. And so the net angular velocity of the cone consists of two separate angular velocities, or vector sum of two separate angular velocities. One is this omega and the other is this phi dot. Okay, so now omega is going to be always in the direction k, and phi dot, if we consider the vector phi dot is going to be directed along the axis of the cone and directed towards the point O at every instant. So the angular velocity phi dot is always going to be like this. I'm just using two arrows to indicate the angular velocity vector, and it's always going to be directed from O prime to O. Now if you consider this vector going from O prime to O, we need to express it in terms of the triad that we have considered, which is I, J and K along this X, Y and Z. So that triad, in order to express this vector along that triad, we need to note that this angular velocity is making an angle beta, okay, with respect to the horizontal. So with respect to the x-axis, it is making an angle beta. Right? So just making sure that I have got the diagram correct. Yeah, it's more or less shown correctly. So you can see that the phi dot is going to be resolved by taking the cosine of the angle beta to give you the component in the x direction, and it's going to be the negative x direction because it's pointing this way, so its component along x is this way, which is negative of the x direction, so that I. And in the z direction, it also has a component, so you have phi dot sine beta k, and in fact this is also negative, right? So in fact the angular velocity is omega minus phi dot sine beta k minus phi dot cosine beta I. So that's the net angular velocity. Keep in mind that when we apply this relation to relate the velocities of 2 points on the same rigid body, then the angular velocity is the net angular velocity of that rigid body. Only then you will get the right relation between the velocities of the 2 points. So that's this vector omega. Next, we've got to find out what rho c with respect to O prime is. Now that vector rho c with respect to O prime is the vector going like that. That is c with respect to O prime. So that's rho c with respect to O prime. Okay. And again we need to resolve this vector along the directions of this triad here. So rho c with respect to O prime, firstly the magnitude is a small r, and then if the angle of the cone is beta, then this angle is beta. So you can then say that c with respect to O prime is r sine beta I minus r cosine beta k. Let me just check. Yes. So that's the rho c with respect to O prime. Okay. So now we can carry out this algebra. Don't think I will need the figures anymore, so let me just carry on with the algebra then. Vc is then equal to Vo prime, which is omega h cosine beta j, plus r sine beta I minus r sorry, this is, I should put the angular velocity first, I'm sorry. So plus omega minus phi dot sine beta k minus phi dot cosine beta I cross the vector rho c with respect to O prime, so cross r sine beta I minus r cosine beta k. Okay, so this is the cross product that I need to carry out in the second term. So I have omega h cosine beta j plus k cross, so if I do a term by term cross product, then k cross I is going to be j and k cross k is going to be 0. So k cross I is going to be r sine beta times omega minus phi dot sine beta. K cross I is j, so put the unit vector. Next we do the term by term cross product of this term with these two. I cross I is 0 and I cross k is minus j. So when we do the cross product, we will have minus r phi dot cosine squared beta j. Let me just check if I have the right expression. Yes, I do. So I will have r sine beta times omega minus phi dot sine beta and then I will have minus just give me a second, let me just see h. Okay, so I can write this as plus omega h cosine beta, and r cosine beta is equal to h sine beta. If you recall from here, we derived r cosine beta is equal to h sine beta. So we will have minus r phi dot, or rather just phi dot cosine beta times h sine beta. Right? And so in the next step we will do r sine beta omega minus phi dot sine beta plus we will have h cosine beta as a common factor in these two terms. So h cosine beta times omega minus phi dot sine beta j. Right? And so you can see that omega minus phi dot sine beta is a common factor here, so we can write this as omega minus phi dot sine beta times r sine beta plus h cosine beta j. That's VC. Okay, so we see that the velocity of C is completely in the j direction, and this is the expression. Now we know that the velocity of C is equal to 0. Vc is equal to 0 due to roll without slipping. And since that's the case, then we have a product of these two terms being 0. Now we know from the original expression that h sine beta is equal to r cosine beta, so that actually if you take that expression and substitute over here, you will see that this expression, in fact we can do that right now, we have r is equal to h sine beta divided by cosine beta. So this is omega, so let me just minus phi dot sine beta times r is h sine beta divided by cosine beta. So h divided by cosine beta is going to be the expression, because if you substitute h or r is equal to h sine beta divided by cosine beta, then this will become h sine squared beta divided by cosine beta, and if you take h divided by cosine beta as a common factor, then you will have sine squared beta plus cosine squared beta. Now this product has to be equal to 0. Clearly h is not 0, that's the height of the cone, and beta, cosine beta, is not equal to 0 either, because we have a cone and the angle beta is an acute angle. So these two, or rather this term h over cosine beta, is positive. So therefore, in order for the velocity of c to be equal to 0, this is vc equal to 0, we must have omega equals phi dot sine beta, or in other words, phi dot is equal to omega divided by sine beta. And that's the kinematic relation that we have been looking for. So this is the relation that we wanted to find out, and by using the rotating reference frame, we have been able to show in a structured formal manner that indeed the velocity, angular velocity phi dot, can be related to omega by phi dot being equal to omega divided by sine beta. The relation between the two angular velocities, as you can see, does not depend on the radius of the cone, rather it depends on this angle beta. Okay, so both h and r showed up in our analysis, but in the ultimate result, phi dot was equal to sine, or rather phi dot was equal to omega divided by sine beta. So h and r do not show up explicitly. Sine beta captures the relation between omega and beta. You can also interpret that as the relation between omega and phi dot is not determined by what is the radius of the cone. So the cone could be a bigger radius, or whatever is the height of this cone. The height of this cone can also change, but as long the angle beta remains constant, then the relation between phi dot and omega remains the same relation, the same ratio. So this was a problem where we did a kinematic analysis to find out what the spinning speed and the speed omega of a cone that is rolling without slipping is. What is the relation between the two? And for that we had to use some kinematic analysis. We used a rotating reference frame. We used the fact that 2 points on the same rigid body have a definite relation between them in terms of their velocities, and that relation includes the net angular velocity of the rigid body. So all these things were combined to solve this problem, and so that this is going to be a continuation of the rolling cone problem that we have started in the previous video, and we will continue with this problem with another set of rotating reference frames in this next video that will come up. So we'll stop here. Thank you.